All right. So we're done talking about vectors. The quantities that are vector quantities in 2 dimensions are the ones that had direction in 1 dimension. What were the quantities, the physical quantities that had direction in 1 dimension? So those are the ones that could be positive or negative. Yep, velocity. Yeah, I'll actually write that as position, and displacement is pretty closely related to position. And then one more, acceleration. Yep, that's exactly right. And so now in 2 dimensions, position, velocity, and acceleration are vectors. And any quantity that is a vector, we're going to indicate that with an arrow over the top. And since these are vectors, each of them will have an x and a y component. And so you can think of the position vector as being a vector made up of px and py. Each of those is just a number. It can be positive or negative. The vector v is the x component vx and the y component vy. And acceleration is same thing, an x component and a y component. In 1D, after we specified 4 quantities, 4 values, and those were the instant corresponding to time equals 0, the instant corresponding to time final, a location corresponding to p equals 0, and a positive direction, then 3 equations hold. VF equals VI plus ATF. PF equals PI plus VITF plus 1/2 ATF squared. And 2A times the quantity PF minus PI is equal to VF squared minus VI squared. Okay, you know all that. But now in 2D, once you choose 4 values, and these are, so 2 of them are going to be the same. The 2 related to time are going to be the same because time doesn't change in 1D or 2D. So we're going to choose the time equals 0 instant. The time final instant. And then the equivalent of the location where the position is equal to 0 is now we're going to choose an origin location for the coordinate system. I guess I'll write that as coordinate system origin. And the equivalent of choosing the positive direction is choosing the orientation of the coordinate system. Once you do those four things, 6 equations hold. And those are, so each one of these, like notice it's exactly the same form as the 1D equations, except we're going to separate each one of those 3 constant acceleration equations into an x component equation and a y component equation. So the first 2 are VFX equals VIX plus AX TF. And then all of these with the y components. So VFY is equal to VIY plus AY TF. So notice that the TFs don't have components, right? Time is still just time. We're going to take advantage of that in a lot of problems, because if you figure out what the time is in the x component, say, you can then use that in the y component equation. Okay, the next 2 are PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. It's exactly like that equation in 1D, but it's just x components on anything that's a vector. And then same thing with, but now with the y components. And then the last 2, 2AX times the quantity PFX minus PIX is equal to VFX squared minus VIX squared. And then the same thing with all y components. So I guess I'll think of these 2 as equation 1, A and B. These are equation 2, A and B. And equation 3, A and B. So these are all based on, you know, a vector form of position, vector form of velocity, vector form of acceleration. Once you have defined those vectors, notice that the equations we're going to use are just regular equations. The reason we can separate them up into an x component equation and a y component equation is because, you know, I mentioned this when we were talking about what vector addition means and multiplication of a vector by a scalar. Because of the way that those calculations are done, you can always break up combinations of those 2 things into a separate x component and a separate y component. Okay, so it has to do with vector addition and vector multiplication that we can break them up this way, but always remember that these equations represent these vector quantities. Okay, and we can always take these numbers and put them back into the vector form. So let's just go through a quick definition of the position vector, velocity vector, and acceleration vector. Okay, so I guess I'll start with position. Remember when we were talking about this stuff in 1D, I drew the train and I said, what does it take in order to put a number to the location of the train? And we figured out that we had to choose a 0 position and we had to choose a positive direction. And so I'm going to go through sort of the same thought process here, and hopefully it'll sort of make sense why we have to choose this stuff with a coordinate system. So here's the train. It's 2D now, so it has to have wings. Okay, so what does it take for us to define a two-dimensional location for the train? Well, you know, right now, until we choose an origin for a coordinate system and an orientation for the coordinate system, you know, we don't have any point of reference for this. But once we choose, let's say, this is where the origin is going to be, and the x-axis is going to be this way, and the y-axis is this way. And this is still particle physics, so we have to represent the location of this train by a single point. So I'll represent it by the center of mass. Okay, so this is the position vector. And now once we know this angle, you could figure out that the position vector is, if the length of this vector is L, the position vector would be L times the cosine of theta, L times the sine of theta. So in other words, the x component of the position would be L times the cosine of theta, and the y component would be L times the sine of theta. And then remember, based on the position, we defined the velocity in 1D, and I'm going to do the same thing here. Do you remember what the steps were for defining the velocity? First, I defined a type of velocity that we never really ended up using very much. What was that? Average velocity, yep. And so in 2 dimensions, the average velocity is equal to the position vector at some time 2 minus the position vector at some time 1 divided by t2 minus t1. And using that definition, you can come up with an approximation for the instantaneous velocity vector as the position at t2 minus the position at t1 divided by t2 minus t1, where t1 and t2 are close to the t that you're interested in. Let's say the desired time. When I was talking about calculations with vectors, I didn't really define division. But does anyone have a guess? Like, all I've defined is addition of vectors and multiplication of vectors by scalars. Based on the definition of multiplication, what would you think it would mean to divide a vector by a scalar? Yeah, that's exactly right. So what you're doing here is you're subtracting this vector from this vector and multiplying it by 1 over the elapsed time. And if you think of it that way, then what you have for the numerator is a vector, right? Because if you add two vectors, you get a vector. And if you multiply by a scalar, you multiply a vector by a scalar, what do you get out? A vector or a scalar? You get a vector out. I know you were going to say that. That's why I stopped you. So it makes sense anyways that velocity would be a vector if position is a vector. Okay. And then for acceleration, the acceleration vector is the velocity at some time 2 minus the velocity at some time 1 divided by t2 minus t1. This is a vector again because you have a vector divided by a scalar. And do you remember in 1D, why was it that we didn't have to talk about average acceleration versus instantaneous acceleration? You guys are just like vibrating with excitement about this. I love it. No, it's because all the problems we're doing, you would have to do that normally, but all the problems that we're going to do have constant acceleration. So if you have constant acceleration, there's no difference between average acceleration and instantaneous acceleration. Okay. So the same thing here. And so that's the definition of position vector, velocity vector, and acceleration vector. So let me give you some common strategies for two-dimensional kinematic problems. So I guess over here, this is the stuff that you should do. And here are some sort of common pitfalls that you should avoid. So first, when an object, in 1D, when an object was up at the highest point of its flight, the velocity was equal to 0, right? In 2D, it's not exactly the same, but it's similar. So when an object is at its highest point, the y component of the velocity is equal to 0. Don't make the mistake of thinking that the x component of the velocity is equal to 0. That would say that the entire velocity vector would be 0 at the highest point. And I think there's a sort of a nice intuitive way to make sense out of it. Well, not very nice, but a good intuitive way to make sense out of that. So think about this. So let's say you have like a tennis ball gun. Do they use those still? So this thing shoots tennis balls for like tennis players to practice without friends. And say that your friend convinces you this is how they lose their friends. Like, why don't you just stand up on this ladder facing away from this tennis ball cannon And it'll be fine because I'm going to shoot this tennis ball so that right at the instant that it hits you, it reaches its highest point, you know? And when this tennis ball reaches its highest point, its velocity is going to be equal to 0. And if its velocity is equal to 0, you won't even feel it, you know? It'll be great. It'll be like a YouTube sensation. And, you know, if you think about that intuitively, you sort of know, like, this sounds a little sketchy. And the problem with it is, the reason it doesn't work that way is the y component of the velocity actually would be 0 there. Okay, it wouldn't, at the instant it's at the highest point, it isn't going up or down, it's going exactly horizontal. But the bad news is that whatever its horizontal velocity was at the instant it was shot out of the cannon, that's the, you know, x component of the velocity when it hits you. And so that could be 60 miles an hour, and that would feel terrible. Okay, so if you ever get confused about what happens at the highest point in two-dimensional motion, think about that example, okay? And think about, like, I remember, was it that I did want to stand up there, or I didn't want to stand up there? It'll just help you make sense out of it. Actually, my little brother, when he was 2, me and my friend were like catching fly balls out of one of these tennis ball machines, you know, like we were standing on the other side of the tennis court, like shooting balls up into the air. And yeah, they come out at, like, you know, 75 miles an hour or something. And my brother just, like, he saw one go and he's like, oh, that's interesting. And he just waddled over, he could barely walk, and just looked right down the tube. And we're just like, no, no, no. And he just got it right in the eye. So that was hilarious. He deserved it. Stupid jerk. He's fine, though. Okay, the second strategy for 2D kinematics is at the instant an object is dropped, the object's velocity is the velocity of what it was dropped from, you know, like a vehicle or whatever. Object's velocity is the velocity of what it's dropped from. So if an object is dropped from a building, you know, out a window, at the instant it's released, its velocity is 0. You know, the building doesn't have any velocity. So both components of the velocity would be equal to 0. If an object's dropped out of a helicopter window, right at the instant that it's dropped, the object has the same velocity as the helicopter. Okay, so like, for example, if an object is, like, a person is riding on something that's going really quickly up into the air and they drop it, the object will actually, it'll start with a little bit of a, you know, with that upward velocity. And so it'll actually go up a little bit before it, you know, reaches the highest point and then starts coming back down. Okay, so that's going to be an important one. Another thing to avoid is so this one, let's see. Go up here to number 1 on the common pitfalls. Make that Vx is not equal to 0. I don't know, just and then number 2, don't assume that Vy is equal to 0 at the ground. This was something that I told you to, not make the mistake of doing in 1D. So the two-dimensional equivalent is, so if an object goes, way up into the air, comes down, hits the ground, at the instant it hits the ground will stop its, it will make its y velocity 0. But we can't assume that in our problems because by the time the objects hit the ground, it's not in free fall anymore. Okay, so we can't assume that in our problems for the same reason we couldn't in 1D kinematics. And then the last pitfall is don't assume the acceleration of gravity changes based on the direction, I guess, the direction of motion. So just like in 1D, I said this a bunch of times until, a couple people just got up and left in a huff, and, I had to call at their parents' house to get a hold of them, whatnot. If the object's going up, the direction of the acceleration of gravity is down, right? 9.81 down. If the object's going down, the acceleration of gravity is down, 9.81. Same thing in two-dimensional kinematics. No matter what's going on, the acceleration of gravity is, for free fall problems, 0 for an x component, 9.81 negative for the y component. Okay. Here's another thing to notice about the problems that we're going to do. Often, problems will have velocity information given by a speed and an angle. Like, for example, a problem will say an object is launched at 50 meters per second, 20 degrees above the horizontal. So when that happens, you'll calculate the velocity vector using the velocity vector is equal to the speed times the cosine of the angle, speed times the sine of the angle. Like in this example, the velocity vector at the instant that it's launched is 50 times cosine of 20 degrees, 50 times sine of 20 degrees. Any questions about that? So velocity, I'm just saying this because velocity is the time, is the quantity that's going to come up most often with. Okay, it's not going to come up so often with position or acceleration, but velocity is going to come up that way all the time. Here's something important to keep in mind, and I bring this up because there aren't really like that many places in first semester physics where your intuition is really far off. You know, like you've seen objects fly around and fall, and um, most of the time your intuition is sort of on the money somewhat. But there are a few places where it tends not to be. Like most people, the way they guess things work is not actually how they work. And so you kind of have to be conscious about those things to try to like create an accurate intuition. Um, so what those equations 1, 2, and 3 say, the way we're breaking them up into x components and y components, is they say that there's no interaction at all between the motion in the x direction and the motion in the y direction. Like that seems a little odd, but as long as there's no air resistance, it is true, you know. If there is air resistance, it's a little trickier. Like, for example, you know, a Frisbee, it's designed to build up a lot of air resistance. That's what keeps it up in the air. And so a Frisbee, if you throw it horizontally, that's going to have a big effect on how quickly it falls to the ground, right? Like you know, if you just drop a Frisbee to the ground, it'll hit the ground a lot faster than if you throw a Frisbee, right? But as long as you can make the assumption about free fall, as long as there isn't a lot of air resistance, whatever is happening in the x component doesn't have any effect on what happens in the y component. So your intuition is probably wrong about the interaction between motion in the x direction and motion in the y direction. If the free fall assumption is valid, there is no interaction. And this is the classic example. Say that you have one person here with a gun. That's a big gun. And yikes, don't mess with that guy. And you have one person here. That person would have to lean uncomfortably far forward unless I move him out. Okay, this guy is holding a bullet, big bullet. What's going to happen if right at the same instant the guy on the left drops the bullet and the guy on the right shoots the bullet horizontally? Your intuition for most people tells you that this bullet is going to hit the ground quickly. This bullet is going to take longer to hit the ground. What the math of these two-dimensional kinematic equations say is that they should hit the ground at exactly the same time. Just the one that's shot out of a gun should hit the ground a lot farther away, you know. That's, I think, am I right? I mean, most people, that seems unlikely, sort of, right? And weird things could happen. A bullet's going so fast that even though it's pretty small and fairly dense, it can build up a lot of air resistance. But I actually want to show two short videos. One is sort of a kind of a stand-in for this experiment, but explained by a well-known physics professor. And then after that, I want to show the Mythbusters clip where they actually rig up an experiment to do this. And you'll see that it really, they get a little bit of difference in how long it takes, but it's very small compared to the length of time these things are in the air. So, all right. Okay. So this is the guy, Paul Hewitt. And he just rigged up this little contraption that's going to sort of kick one pinball out at the same time that it drops the other one basically straight down. Whoops. Is that coming through? That's not, is it?
Okay. Watch this gang close.
Oh, there we go.
Surprise. I got another but essentially take down a little bit downish. This one goes outish. Now I'm going to do them both at the same time. When I do them both at the same time, you guys got to figure out, hey, we hit the ground or the one in the air for a longer time. You know why? The gravity going to start to pull it. I didn't know you would gravity not. Let's try it. If you hear all for this course, Rick say, you I'm going to go all in your class. I'll say, sharp class, honey. Sharp, all right? All A. Do you hear this? Then you gotta do your homework. Okay? Here we go again. Here we go. This moment may be very important. A lot of you writing in it. All right, here we go. Here we go. Listen. Now you can get a better look at this thing. Slow motion, here we go. Okay. Gravity holiday because it's
So that one, I think when I see this, I think the same thing that you do, like, well, that's great, but that's not a bullet. Let's see the bullet, you know? So yeah, Mythbusters did the, let me see if I can find it. Bullet fired versus dropped, part one. I fell for this in the day class and I'm not falling for it again. It takes like half an hour if I start at part one. Let's see. No, it looks like I'm falling for it, but I'm not. Is part two. It has like 5 parts. So I guess I could do it this way.
So far, testing whether a slug fired at a
Okay.
The Misters are testing a real doozy. Everything's hot, ready to go. Bullet shot versus bullet dropped. But a malingering magnet is as soon as it's just staying at stand. Awesome. Oh no, it's gone. We've got a new little solenoid in there which will whoop, get out of the way and let the bullet drop. All we got to do is try it once, get our timings right, continue it. Releases. Release. Three, two, one. Let's see. There's a training problem. So the most difficult thing about the fired bullet airborne at exactly the same time, and we make the result that we want to see happen. Use the brainstorm. We're not even seeing instructing. Which is slate. As for trying solenoid, slugs are now staring failure square in the foot is snatches victory from the jaws of defeat. Pulling metal. Yeah, that's what I mean. There needs to be some sort of a clip. So the trick minutes needed. Oh, it's good. It's good. It's 1/3. Go do this now. Which means rolling up the room 260 out. So, okay. Adam lays down a runway of white paint camera to clearly see and measure bullets. At dawn. never make predictions. That's awesome. Inspired.
So can you see that in that picture? That just the bullet that's shot out of the gun comes in and rips her. As you see her bullet popped. In real time like that, you can't see any difference at all. And that's sort of the story, you know. It ends up being off by a few milliseconds. It's the same time.
So after 1 week in Peru to check the drop zone. And the results are simply ripping. Can't get much closer than that. Oh, I can't wait to see the high speed. Right zone. I think this might impossible to happen. But Adam and 3677 minus 3915 equals 230 divided by. Dude, the difference 9.6 mils less I can make out. So after days of brain teasing tests.
So that's pretty cool, isn't it? It's you know, in practice, as long as you can make that free fall assumption, the motion in the x direction, whether something's moving fast in the x direction or not moving at all, doesn't have any effect on the motion in the y direction, and vice versa. Okay. Any questions about that? Let me go through a set of steps. I did this in one dimension for one-dimensional kinematics too. Just go through a set of steps of how to proceed on these problems, and then I'll start doing some example problems. And I think, you know, today through at least most of next class, we'll just be working on example problems. Okay, so steps for using the constant acceleration kinematics equations in 2D. The first thing is we're going to choose those 4 values that we have to specify. So choose an instant corresponding to time equals 0. Choose an instant corresponding to time final. Choose an origin location. And choose a coordinate system orientation. Just like in 1D, you can use these for free fall problems or other types of problems. Most of the problems we're going to do are free fall problems. So for free fall problems, choose the y-axis up. And how you make these choices is just the same way that it was in one dimension. the choosing the location of the origin and the orientation of the coordinate system, those things are arbitrary. You can solve the problem with a lot of different combinations of those. But you can't solve the problem if you choose the wrong instance for time equals 0 and time final. So those have to be chosen based on when you know information and when you want to find information. Okay. Second, list the variables that you know and the variables that you want. So remember in 1D, I would just always go through the list in the same order. I do PI, PF, VI, VF, A, TF. You can do that in 2D too. There's just a lot more values you have to worry about. So let's see. Now there's 2 possible PFs, 2 possible PIs, 2 possible VIs, 2 possible VFs, 2 possible accelerations, still only 1 time. So that's, what's that? 13 possible values, I think. Something like that. Let's say 13. And again, what you're looking for is you're looking for an equation that has the variable that you want in it, and every other variable in the equation is known. Okay. So 3, find the equation that contains the variable you want and all the other variables in it are known. So in 1D, do you remember what comes after this in 1D problems in the steps that I listed? There was sort of an optional or possible next step. That's if this doesn't work, then you need to go back and find some intermediate variable, one that you're not looking for specifically, but that then you can use as a known variable once you solve for it, to solve for the one you do want. And in 2D, we have the same thing. In 2D, in fact, this is going to happen a lot more often. So often, you're going to need to find an intermediate variable The first one you want to try is time final. If you don't already know time final, more than half the time, more than half of the problems that we're going to do, that's the one that you're going to need. The reason finding time final is so useful is that's the one variable that crosses from the x component equations to the y component equations, you know? So like if you're trying to find like horizontally how far an object goes before it hits the ground, well, you can figure out using the y equations how long it takes for this object to go up and hit the ground. And then that time final is still valid when you go to the x equations to figure out how far horizontally it traveled in that time. So if that doesn't work, then try acceleration. That's only true in free fall problems. And then after that, you're on your own.
In a free fall,
Mm-hmm.
the acceleration will be still negative 9.881
Yes.
for x and y.
So the acceleration is always going to be 0x and then negative 9.81 y. As long as you choose your y-axis pointing up. Any other questions? Okay, let's go through a problem. So let's say that this is supposed to be like a pitcher. He looks terrible. Actually, the velocity that he's throwing it with suggests that he is terrible. Okay. I don't know. He's throwing it with his bad hand or something. You got to get the stirrup pants and stuff. Okay, and the ball is released with a speed of 20 meters per second. At an angle of 25 degrees above horizontal. How far away will the ball hit the ground? To solve this, you need to know one more thing. You need to know how high the ball is at the instant it's released. So let's say that's 1.5 meters. Okay, so the two values that we have to get right are the instant corresponding to time equals 0 and time final. What do we want to choose for those two? What do we want to choose as our time equals 0? Yeah, the instant he lets go of it. And we want to choose that one because we know the speed at that time and we know the angle. So time equals 0 is going to be at the instant it's released. And what's going to be time final? Yep, hits the ground. And now for the coordinate system. For the origin, you could do this a bunch of different ways. One way that's useful a lot of times, especially if something is going to end up hitting the ground in the problem, is put the origin of the coordinate system on the ground directly beneath where it's, where the motion starts. So the origin is I'm going to do it with the origin right there on the ground, directly beneath where it's thrown from. And for the coordinate system orientation, we know we want the y-axis to be up, but we also need to specify the direction of the x-axis. We know that it's going to be horizontal somewhere, but we could do it with the x-axis pointing, you know, a bunch of different ways. So let's do it, and this is generally what you're going to want to do. The y-axis is pointing up, and the x-axis is pointing horizontally in the direction of the motion. Okay. And now we can start to list out what we know and what we want. Do we know either component of the initial position? So at the instant it's released, so here's the coordinate system finished. X-axis goes this way, y-axis goes this way. At the instant it's released, do we know either component of the position? X equals 0, yep. Do we know the y component? Yep, 1.5. So pi, I'll just write it as a vector like this, is 0, 1.5 meters. Do we know either component of the final position? Well, we know that at time final, it hits the ground, right? And we know the ground is 0y. So we don't know the x component. That's what we're looking for. So I'll put pfx over here. That's what we're trying to find. But pfy has to be equal to 0. Do we know either component of vi? We don't yet, but we can figure it out. We know that there's a speed of 20 meters per second, and it's being thrown at an angle like this, where this angle is 25 degrees. And so that vector in this coordinate system is 20 times cosine of 25, 20 times sine of 25. So VI is 20 times cosine of 25 degrees, 20 times sine of 25 degrees. And that is 18.12 meters per second x, 8.45 meters per second y. Do we know anything about the final velocity? Nope. We know the acceleration is 0, negative 9.81. And do we know the time final? Nope. All right, so do any of those 6 equations, 1, 2, or 3, A or B, do any of those have PFX in them, and anything else in it appears in the known column? So we know it has, you know, we have to be looking for an X equation, or else we wouldn't have PFX in it. Equation 2 almost works, but we don't know time final. And equation 3 almost works, but we don't know VFX. And equation 1 doesn't work because we don't know V final X. Well, that one isn't even close to working. So nothing works. That means that we're going to try to find an intermediate variable. So is there, so no equation works. The question is, can we find, and I said the intermediate variable we should look at first is time final. So can we find time final? Is there any equation that has time final in it and everything else in it is known? And for that one, we can use equation 2b, the y. So we can use this equation. PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 1.5. Oh, and by the way, so I've been keeping my units in all the calculations up until now. Now at this point, I'm going to stop doing that, and feel free to do that too. I want you to put units in your final answers, but you can skip all the units. I mean, you can keep doing it if you want, but it just saves some time to leave them out. So I'm just going to write this. 1.5 meters is 1.5. VIY is 8.45 TF plus 1/2 times negative 9.81 times TF squared. How do we solve this equation? Quadratic formula. When can you, so sometimes when you have the variable you're looking for squared, you can just solve it with a square root. When can you solve it as a square root, and when do you need the quadratic formula? What makes us need the quadratic formula here? Well, you could do it as a square root if all you had was a constant and something to the second power. This middle one, this linear term, is the one that makes it so you can't just take a square root. So if you ever have something squared and something with a linear term, that's when you have to use the quadratic formula. So this is A, this is B, and this is C. If you solve that, you get TF is equal to 0.801 plus or minus 1.024. And so you get one negative answer. And we don't care what that is. We already know we can reject that because we're never going to deal with negative times. And the other answer is 1.89 seconds. And now can we solve for, what are we looking for? PFX. Yeah, now we can use equation 2a to solve for PFX. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to, what was PIX? 0, yep. What was VIX? Yep, 18.12 times 1.89 plus 1/2 times what's AX? 0, yep. And so this all goes away. This goes away. And you end up with PFX equal to 34.27. 34. Okay. So the ball hits the ground 34 meters away horizontally. Any questions about that? All right. So next class on Wednesday, we'll just spend maybe the entire time just working through problems. I'll do a couple, and then you guys will do a couple in groups. Okay.